right, so we're going to work through some examples today dealing with interpreted spectra and also talking about like some complex splitting. I think that won't be too bad once we get to that particular example. And then we're going to talk about how to assign spectra, and then all of our interpretation is going to be on what we already know. So splitting patterns, chemical shifts, and integration, and things like that. So we got 4 molecules that we're going to look at. So these are the 4 molecules that we're going to look at. Like the only one that's going to be a little bit complicated is going to be the first one. And that's because it has a chiral center. And so when you have a chiral center, let me bring the other, right? These are all our non-equivalent protons. When you have a chiral center like this, what you'll notice is that the 2 hydrogens here are non-equivalent. And so we call that, let me share my iPad so I can give you some notes on that right quick. So when you have a chiral center, can y'all see my screen?
Yes.
All right. So if you got a chiral center here, right, the hydrogens that are adjacent, which will be on this carbon right here, we call those hydrogens, you can see them here, they're different. We call them diastereotopic. Right, they're called diastereotopic hydrogens. The reason that they're called diastereotopic is because if you swap either one of, just like we did the test for equivalence the other day, if you swap either one of those hydrogens out with another atom, you will generate a diastereomer, right? Do y'all remember that term from when we first started talking about chirality? And we talked about enantiomers and diastereomers. So these hydrogens right here, we call them diastereotopic, right? Because if you were to test for equivalence, each one of those hydrogens will give you a different diastereomer, right? And so because they're next to a chiral center and because they're diastereotopic, they're going to give you 2 different signals. So each one is non-equivalent. Right? So each one of those is non-equivalent to each other, right? And that matters when it comes time to split. When it comes time to look at the signal and see the splitting pattern, that matters. So we're going to talk about that a little bit later. So let me go back to the PowerPoint, and then we're gonna continue, right? So you have all these molecules, and so here I have all the different protons color coded, all the different types, right? And the same in the second example, all the different types of non-equivalent protons are color coded, right? And then here, these are also all non-equivalent, and then here these are all your non-equivalent protons, right? That should be a proton here at bromine, and then here by the OH. Both of those will be non-equivalent as well. All right, so let's look at the first spectrum. And this is the first spectrum. Now let's look at the first thing we can do immediately is what? What can we look at immediately to kind of start ruling some stuff out? Right, you got a couple of choices, but one of the first and the quickest thing you can do to start ruling out stuff is to look at what?
How many peaks there are?
How many signals? That's exactly right. So you have 1, 2, 3, 4, 5, 6 signals. And then down here, you have in this molecule 1, 2, 3, 4, 5, 6, 7 signals. So you know it's not going to be that. Here you have 1, 2, 3, 4, 5 signals. So you know it's not going to be the epoxide, right? And then here you have 6 signals as well, but there's something that's going to give the benefit to this molecule. And I'm going to show you. Like, do you see these hydrogens here on the double bond? Where would those show up? If you remember from yesterday when we talked about the different chemical shifts, where do hot protons that are attached to alkenes normally show up? Does anybody remember? No? Okay, so they show up somewhere between 4 and 6, right? And then if you look between 4 and 6, you only see one signal and it's only integrating for one proton, right? So that kind of rules out this molecule too. So what we're left with is this molecule, right? It matches the number of signals, 1, 2, 3, 4, 5, 6 signals. And then now let's see if we can figure out what's what based on the integration. All right. So the NH2 and the OH protons are here, right? You see that? That's integrating for one hydrogen. This is integrating for two hydrogens. And so the NH2 is here and the OH is here. We can pick those out right away because remember, I think I said it on Wednesday, those protons don't split, right? They don't couple. And so they don't get split into two lines or triplets or doublets or whatever, right? They remain singlets. So you can see here that those are those two protons. Now let's see if we can walk down the rest of them. So here we have a signal at 1 that's integrating for 3 hydrogens. Which set of hydrogens does that match?
CH3.
The CH3 right here. And if you look at the chemical shift, right, it's at 1, which is representative of a simple alkyl proton. Are you following that? Right, so the location tells me that it's the CH3, but then the integration says it's the CH3. And now let's look at the splitting pattern. What is this signal split into? Is it a singlet? Is it a doublet? Is it a triplet? Is it a quartet? It's a doublet, right? And that, so that means that what, it matches the n+1 rule. That's what we use to determine that, right? So n+1 is 2. What does that mean? It means that whatever protons are responsible for this signal have how many neighboring protons?
1.
1. So you see the CH3 here has 1 proton next door, and so it should be split into a doublet. That's how we can match that signal with this CH3 with confidence. All right. Any questions about that signal or the NH2 or the OH? I'm saving up. Go ahead.
I want to clarify. So when you have chirality, the adjacent hydrogens will always be different or non-equivalent.
Yeah, if you have like a CH2 that's adjacent to that chiral center, then yes. This, it won't matter. You can't make a diastereomer over here because you're going to have 3 different 3 hydrogens that are equivalent. But here, if you swapped out either one of these with a different atom, you get a diastereomer.
Okay.
Yeah. Right, because if you change this hydrogen to another atom, this becomes a chiral center also. On this side, if you change any one of these hydrogens to a different atom, this still won't be a chiral center because you'll still have two groups that are the same. Right, you'll still have 2 hydrogens, and that in order for something to be chiral, you have to have 4 different substituents. Right, so something, a carbon like this would definitely become a chiral center if I took off this H and say put a chlorine there, or a bromine, or some other atom. All right. So are we okay with this? Why this is a doublet? Why it shows up where it shows up, and the integration.
Yeah.
All right.
Yes.
Okay. All right. Let's do this proton right here, the turquoise proton. This one. How should that be split? What do you think? And where should it? So let's think it in order. First of all, where should it show up? Secondly, how should it split? Thirdly, what should the integration be? Those are 3 things that we're going to always do for each one of these signals. Where it shows up on the spectrum, the splitting pattern, and then the integration. So what do you think?
Dr. Rector, I have a question.
Go ahead.
So with that being CH3,
Okay.
Would those three H's be one thing, or would you count them as three H's?
No, they'll all be equivalent and they'll all show up under the same signal.
Okay.
Yeah, it's rare to have. The only time you start generating, like if you have multiple hydrogens on the same carbon, the only time that they're going to be non-equivalent is in a situation like this, where you got a CH2 that's next door to a chiral center. But for 99% of the time, all three of these hydrogens are going to be equivalent to each other. So they're going to show up under, they're going to be represented by the same signal. All right, so what about the turquoise or the teal colored hydrogen? Which signal? So we got three signals left to choose from. Which one do you think is representative of that? So you got to think about where it's going to show up. You got to think about how it's going to be split. And you have to think about the integration. So what should the integration be for the signal? One, right? Integration tells us how many hydrogens a signal represents. So the integration should be one. All right. Where should it show up? Because it's on the carbon that's attached to a hydroxyl group. So where should it show up? Downfield or upfield? Downfield, right? Further downfield. So it's got to be one of these three. Now let's think about the splitting pattern, because that's how we'll be able to distinguish between this proton and the other protons, the other two protons that are left, right? So what should it be split into? How many neighbors does it have?
It has 5.
Five, right? 3 on this side and then 2 on this side. Is that right?
Mm-hmm.
So the signal should be split into how many lines?
6.
6. Can you see that? I think I have a zoom in here somewhere. Hold up. Let me do this. Right? Can you see that the signal here is 1, 2, 3, 4, 5, 6 lines? And then over here, these two signals are 4 lines. You see that? 1, 2, 3, 4. Are you following that?
Mm-hmm.
Right. So of these three signals, which one do you think represents the teal proton? It's got to be this one, right?
No, it's 6. Yeah.
Yeah, it's got to be this one. It matches. It shows up between 3 and 4, which is normally where a proton that's adjacent to, or a proton that's on a carbon that has a heteroatom like oxygen or sulfur or nitrogen shows up. And then the integration is 1, and it's the splitting pattern is split into 6 lines, right? So this matches for this proton. So that's how we know that that's the signal for that hydrogen. All right, any questions so far?
Are you able to show all the molecules that we had as like options again?
Yeah, I can. I have to. Yeah.
Okay, I was confused on like last one you said that that is 6 signals. And like I
Yeah.
don't, could you like circle the 6?
Yeah, so it's here. So each one of these, that's 1, 2, 3. Actually, it's 5 signals. 4 and 5. It's 5 different types of protons on there.
Okay, yeah. I thought it was 5. So.
Yeah, sorry about that. That's my fault. All right. Any other questions? All right, now go ahead.
Okay, so the molecule right next to the benzene or the cyclic molecule, so the dark blue hydrogens, those will be counted separately, right?
In this case, no, because this is not chiral.
Oh,
If it was a chiral center, then yes.
gotcha.
But because this is not a chiral center right here, because it's racemic, then they're not going to show up like that.
All right.
That's a great question. That's a great observation. All right. So let's go back to, let me erase all this stuff. And then we got to figure out why these other two protons look the way they look. All right. Is this okay? Is this clicking so far? I know NMR can be kind of, it's very challenging. I'm trying to keep it to the, not necessarily the basics, but I'm trying to keep it to where we can just grasp onto it and not get too overwhelmed. Let me share my iPad again so we can talk about this last set of protons. All right. So the last set of protons